Right, the next gas law we're going to take a look at will involve a container that has a constant volume, and now we're going to be pumping more air into it. So we're starting off with 1 mole of gas in the container, and the pressure then is 100 kPa. Now, if I pump in some air in there, I can get the pressure to become 200 kPa. How many moles of gas will be in there now? Right, you guessed it, 2 moles. So you notice I doubled the pressure by doubling the number of moles of gas. And if I put in more gas, I could probably burst that container. And let's say that it took 600 kPa to burst that. How many moles of gas would be in this now? Well, it'd have to be 6 moles. And we can answer that very easily by looking back at the first diagram. So here we have another gas law relating pressure and the amount of the gas. Now the amount of the gas is not in grams but in moles. So we have P1 over N1 equals P2 over N2, another direct proportion. And this one is called, and you might recognize this fellow, we've seen him before, Avogadros law. Even though it's not that important whose law is whose, it's really the application of them which are going to be asked to complete. Now, next situation we have is a container again with a constant volume, but this time you notice we're taking its temperature. So it's at 300 Kelvin and we have 100 kPa. So what would happen to it if I were to heat this? What do we see happening? To make the pressure go from 100 kPa to 200, I have to double my Kelvin temperature. Now you notice I'm not doubling the centigrade temperature. In fact, the centigrade temperature is going up more than 10 times. But the Kelvin temperature is only doubling. So the increased pressure is due to those particles moving a lot faster, creating more collisions and more violent collisions with the walls of the container. And eventually we'd get to 500 kPa, and that would burst the container. Now, what temperature do you think we needed to get to that? Again, if we compare our first diagram to this one, we can see that the pressure would go from 100 to 500 kPa, so the temperature must be going from 300 to 1500. And this is going to give us the law of Gay-Lussac, which is the relationship between pressure and temperature, another direct proportion. Now we can put all these gas laws together. I'm just going to put them all down here again for you. We can combine them all together in what we call the combined gas law, which would look like this. And this is really the only one we have to use for all of these problems that we're going to see in this lesson. If any of these factors aren't changing or they're not even mentioned in the problem, we're just going to eliminate them from the formula. So let's check out the first problem. So the helium in a 250 milliliter balloon exerts a pressure of 800 millimeters of mercury. What pressure will the mercury exert when its volume is reduced to 125 millimeters? So the first thing we want to do is copy out the data and label it. This is real important so you know exactly what you're doing. Now you don't have to go back up and read the problem. Next step would be to write the gas law. So I'm going to write down the entire combined gas law, but then I'm going to cancel out any factors that are constant or weren't mentioned. Now in this case, the temperature and the number of moles weren't mentioned, so I'm going to cancel them right out. And then what am I left with? I'm left with a part of the gas law that I have to use. Now you may recognize this as Boyle's law, but that isn't that important. So I'm going to now solve for my unknown, which is P2. And I do that by dividing by V2 on both sides. I plug my numbers in and I get 1600 millimeters for an answer. Now one way to check on this is to see how the volume has changed and predict what will happen to the pressure. So we see that the volume went down, so the pressure should go up, and this seems to fit. Alright, let's try another problem. Here we have a balloon with a volume of 120 milliliters at 17 degrees centigrade. What will the volume become when the temperature becomes 34 degrees centigrade? So we copy out the data and label it. Write down the gas law, cancel out the units that we don't need anymore. Cancel out the factors that we don't need anymore from the equation, and solve it. So let's see if you can solve this one on your own. So I might want to pause at this point in time, and then come back and see the solution. Okay, here's the solution now. So I copy out my data. You notice that I convert my centigrade to Kelvin. If you didn't do this, you would have got the wrong answer. I'm writing down my gas law. I'm going to cancel my constant factors. In this case, it's moles and pressure. That leaves me with Charles' law. I'm going to take Charles' law and solve it for my unknown. So I'm going to cross multiply. This is what I get when I cross multiply. And now I'm going to divide the T1 out of there. So I wind up with V1 T2 over T1 equals my unknown. I'm going to plug in my values and I get 127 mLs for an answer. And that's what I would have expected, because if the temperature goes up, then the volume should go up. So how did you do? All right, let's try another problem. Now in this case, we're going to be using more factors. So here we have a gas occupying 225 milliliters at 27 centigrade and 100 kPa. What volume would the gas occupy at standard temperature and pressure, STP? Now standard temperature has to be 0 centigrade or 273 Kelvin, but it can be any of those standard pressure units we saw early in this lesson. So let's copy out the data and label it. So we have a lot of data here. And all right, now I'm going to write down my gas law. In this case, the only thing I'm going to be canceling out is N. That's what I'm left with. Now it's just a larger ratio. I'm going to cross multiply and divide. And this is what I have so far. Now I'm going to finish this up on the next slide. So here's where I left off. I have my gas law, which I've cross multiplied. Now I'm going to solve for V2. So to get V2 by itself, I have to divide by P2 and T1, and it'll cancel out of there. And now I finally have it. So at this point in time, I plug in all my values and then solve it. And you notice that all the units will cancel except for mLs. And I get 202 mLs. So now let's take a look at another way we could do this. This is called the logic method, where we just figure out what will happen to our unknown, whether it'll get larger or smaller, and then we just make fractions out of the data to make this work. So these are the same three problems that I just went through, but looking at it logically. So here was the first problem, and there was the data. Okay. Now, here was how we figure out what's going to happen. If the volume goes down, which it is, then the pressure has to go up. And that tells us that P2 has to be greater than P1. So P2 is going to be bigger than 800 millimeters. What I'm going to do is make a fraction of my two volumes that's greater than 1. So I'm going to put the larger volume on top, smaller one on the bottom. Then I'm going to multiply this by P1. So when I do that, what I get for an answer? I get the 1600, just as I got using the formula. This is why it's called the logic method, because you logically figure out what should happen to your unknown, and you just make the math work for you. So let's apply this to the next two. So this was the second problem that we had. It was our data. So see how the temperature is going up. Okay. If the temperature goes up, then the volume should go up. That means we need a fraction greater than 1, just like we had before. So my fraction would be 307 over 290. That's greater than 1. And I get an answer of 127 milliliters. And we can even apply the logic method to more of the gas law, as we saw in the third problem. So here's that gas law again, and here's our data. In this case, we'll take each change separately and see what would happen to the volume when each of these changes happens. So the first thing we'll look at is pressure. If the pressure goes up, then the volume should go down, which means we need a fraction that's less than 1 out of my two pressures. For temperature now, since temperature is going down, I need a fraction also that's less than 1 for my two temperatures. So then when I set them up, it would look like this. And there's my answer. Okay, looks pretty good. All right, so this is the end of the first lesson. So what you should do at this point in time is either try some of the problems out of the text, or you could even go to the Connect assignment and try some of those.